as a dream cycle or ideal cycle. Okay, so that we have covered last lecture. So today we want to have the first of all the review will take for 15-20 minutes what we have taken and what was how much of you understood that way overview. So who will tell the limitations of Carnot cycle at one unmute and tell the limitations of Carnot vapor power cycle. Somebody have to take initiative, take lead, and who is presenting?
Yes, sir.
Kunal. Am I right, na?
Yes, sir.
Uh,
Yes, sir.
tell one by one. Loud, little bit slowly, so that everybody will understand.
Superheating is not possible due to isothermal heat addition.
Okay, superheating is not possible due to isothermal heat addition. Good. Okay, one more from your side. Others, you give chance two from each. Okay, one more from your side.
Condensation is
Good,
not
very good.
completed.
What condensation is not completed? It is
Completed.
partial. Is
Then
partial. Uh, why it is partial
there is
condensation?
because there is mixture of vapor and liquid.
Okay. Then, next.
There is no such compressor which will compress mixture of liquid and vapor.
Good, good, very good. Due to that,
Then
this Carnot
due,
cycle. Okay. Good, good. Oh,
due
go
to
ahead, go ahead.
due to incomplete condensation, compressor has to deal with mixture of liquid and vapor.
Okay,
Then last
good.
one is the compression and expansion process are assumed isentropically, but due to friction
Friction.
present in compressor and turbine, this process is actually not isentropic.
They are in anisotropy. Good. Okay, very good. So everybody understood these limitations of Carnot cycle. Due to that, we have switched over to our Rankine vapor power cycle. So because it is not practically possible cycle, because of the so many limitations, or main limitation is there that condensation is not complete, and therefore what we have to go for, condensation is not complete, therefore here so condensation is not complete, hence
Uh, incomplete compressor has to deal with mixture of liquid and vapor.
mixture of, correct, very good. So compressor have to deal the mixture of liquid and vapor, and such kind of compressor is not not manufactured till date. Till date means at the time of Carnot also it was not manufactured. Therefore, we are switching towards the which cycle? Vapor power cycle. Sorry, Rankine vapor power cycle. Okay. So Rankine had made some changes in this Carnot vapor power cycle, and afterwards I think we have studied. Before that, we have studied the efficiency of Carnot cycle. Correct. So is screen visible? That notebook first page is visible, na?
Yes, sir.
All notebook is not visible, but all pages are not visible. Okay. Then I think we have switched over to which cycle? Next cycle. Anybody? Rankine vapor power cycle. And what Rankine has made changes? Anybody?
Rankine has replaced two isothermal processes of Carnot cycle by isobaric processes.
Okay, that is to heat addition. He made it as a isobaric, that is at constant
Isobaric.
pressure. Okay, and heat rejection in condenser also made as a isobaric. Okay, at constant pressure. So depending on that, we have gone for the diagram. So only because condensation will be complete or incomplete in Rankine cycle. What's
Complete.
about condensation? Condensation will be
Complete.
complete, and due to that, which device we have to use now for compression of that
Pump.
liquid? If condensation is complete, means we are getting pure liquid, and to compress the pure liquid or to increase the pressure of pure liquid, which device we are going to use? We are using
Pump.
anybody pump. Okay, only then replacement of whatever the schematic we have drawn for Carnot cycle, in that compressor only we have to replace by pump. Correct, am I right? Okay, and therefore all devices are remain same in this Rankine vapor power cycle: boiler, turbine, condenser, and this pump. Okay, and then okay, the remain now heat addition in boiler is now not isothermal, it is become isobaric. 1 to 2 heat isentropic expansion in steam turbine as it is, because pump and expansion and compression we have kept as it is, though they are the limitations of Carnot cycle, but still we have that Carnot also, Rankine also continued with these processes, means continued with the same limitations. So limitations of Rankine cycle will be same as that of the Carnot cycle, that is turbine expansion and compression assumed as isentropic, but in real case it is these expansion and compression are not isentropic. Then 2 to 3 is their heat rejection in condenser. So it happens at here at again at isobaric condition at constant pressure. And 3 to 4 is their isentropic compression in pump. Okay, and 4 to 1 is what? Boil heat addition in boiler. Okay, then PV and TA diagram we have gone for. Now Carnot cycle is bounded by this curve. So this is diagram is visible. PV diagram, is it visible?
Yes, sir.
Okay, so Carnot cycle, this is our saturated curve is there. Okay, it is critical point where the here plus arrow is there, that is marking arrow is there. So this is will be acting as a, here I am making this fluctuating arrow. So this will be the critical point. Then this will be saturated liquid. This will be saturated vapor and critical point. Then here at point 1 to 2 will be isentropic expansion in steam turbine ST. Okay, and 2 to 3 is there. 2 to 3 is there. It is going to be condensation, that is heat rejection in condenser. It happens at isobaric condition or at constant pressure. Okay, and 3 to 4. But as the condition is 1 minute. Just one. I will just one important phone call. Is it? Hello, hello. हाँ, कोण आहे? अहो चालू आहे कॉलेज, 5 वाजेपर्यंत असते, 4 वाजेपर्यंत असते. या की तुम्ही, काय मला विचारत नाही. कॉलेज यायचं असते, धडकायचं असते पटकन या, 4 वाजेपर्यंत. हं. Okay, so at 3 to 4, 3 to 4 is there. It is going to be isentropic compression in pump. But as the condensation is complete now here at this is point number 3, we have to always show on this particular liquid line, because if condensation is incomplete, then we can show here. But here, as condensation is complete, point number 3 should be shown like this. Then afterwards, compress expansion. Opposite to that, we are going for the compression, and here this point. Therefore, 4 point it should be come outside this curve, because now there is no restriction of isothermal condition. If isothermal condition is there, whole cycle we have to bind in this inside this saturation curve. Okay, but due to this condition now, isobaric condition, we can make this point number 4 outside also. Okay. Now there are TS diagram. If you draw the TS diagram, nature of constant pressure line in our TS diagram is like this. So here it is like this, inclined, then afterwards phase change remaining constant, horizontal line, then inclined line. So inclined line, horizontal line, and inclined line. Okay. So this is the pressure related to boiler, and another is the pressure related to condenser. So these are the one is boiler pressure line, another is condenser pressure line. So now, depending on situation, if the steam is wet, then point number one will be come in the region of wet region, where there is a mixture of steam and water or vapor, steam and liquid. Therefore, point number one is in the wet region. Afterwards, isentropic expansion. Therefore, as 1 to 2 is isentropic, on x-axis we are having entropy. Therefore, complete vertical line. Okay, then 2 point we are getting, so 2 to 3 complete condensation in or heat rejection in condenser, or complete condensation in condenser. Then remain whatever the vapors are there, they are get condensed, they are get converted into this liquid. Okay, and to here at point number 3, what will happen here? Compression will start, as it is completely condensed and it is pure liquid is there, and to compress the pure liquid or pure water, we are having one device. That device we are calling as a pump. Okay, so this pump is, so this isentropic compression in pump. So pump is compressing isentropically, therefore 3 to 4 vertical line. But up to the which pressure line? Boiler pressure line. So 3 to 4. But when that water will be here supplied to the boiler, what will happen first? First of all, the water, the heat we are giving to the boiler, it is utilized to increase the temperature up to saturation temperature. Okay, and when saturation temperature will reach, the phase change will start. Okay, and then after temperature remaining constant. Okay, so during this phase change, temperature is also remaining constant, already pressure is remaining constant. Okay, and then phase change, whatever the heat we are supplying, that is called as latent heat, is absorbed by that particular fuel, and then afterwards it will get liquid is converting into vapor. Okay, if it is wet, some part is remained of water to be not to so that some part is remained as a water only. So therefore steam will contain some water particle. Okay, and my 90 to 95% vapor and 5 to 10% moisture, that steam may call it as a wet steam. Okay, and afterwards this wet steam we are supplying, but generally for power purpose we are going for superheated steam. Then different diagrams are there. Okay, so 4 to 1 isentropic heat, so we are gone for. Then 1 to 2 is there, it is going to be now here dry and saturated. Steam entering to the turbine is dry and saturated. Okay, and then 1 to 2, point number 1, instead of that wet, point number 1 is in the region wet region. If it is a dry and saturated steam we are supplying to the turbine, then in that case here point number 1, it should be always in the on the saturated curve. And then steam entering to the turbine is superheated. Then what will happen? Point number 1 should be in the superheated zone, but in nature of constant pressure line is inclined, therefore it will occupy on the inclined line. And point number 1 will be here on this one superheated zone. From that it will go for the vertical expansion, isentropic expansion, 1 to 2, then 2 to 3 as usual. So only there is a change in this point number 1 depending on the steam quality. Sometime wait, point number 1 here, but diagram will little bit going to change. So here when steam is applied to the turbine is superheated, then this will be 4 to A. If you go for it, now that presentation is not meeting. So 4 to A we can say it is the isentropic expansion. Okay, and then 2 to 3 is the isentropic expansion. Then 3 to 4 is the superheated expansion. 4 to 5 is the superheated expansion. 5 to 6 is the superheated expansion. 6 to 7 is the superheated expansion. 7 to 8 is the superheated expansion. 8 to 9 is the superheated expansion. 9 to 10 is the superheated expansion. 10 to 11 is the superheated expansion. 11 to 12 is the superheated expansion. 12 to 13 is the superheated expansion. 13 to 14 is the superheated expansion. 14 to 15 is the superheated expansion. 15 to 16 is the superheated expansion. 16 to 17 is the superheated expansion. 17 to 18 is the superheated expansion. 18 to 19 is the superheated expansion. 19 to 20 is the superheated expansion. 20 to 21 is the superheated expansion. 21 to 22 is the superheated expansion. 22 to 23 is the superheated expansion. 23 to 24 is the superheated expansion. 24 to 25 is the superheated expansion. 25 to 26 is the superheated expansion. 26 to 27 So I think I have lost some network from my basic device. So now I am audible through this, na? I have
Ye-
started my mobile. Am I audible?
Yes, sir.
Okay. So here, point number, I think screen is not visible now, na?
Yes, sir. Not visible.
Okay. Is it visible now? Okay.
Yes, sir.
Okay. So 3 to 4 is okay. So this is our diagram. So one, this is 4 to 1 will 4 to A will be also sensible heat. Then this will be again, we can say it as a phase change, latent heat, and again superheat. So heat addition in boiler, it will be consisting of, in this case, superheated case. And this is first of all latent heat, then afterwards sensible heat, then afterwards phase conversion, latent heat, afterwards superheat. Okay, so this diagram also we have seen on that day. Then afterwards we have seen the HS diagram. So it is one of the very important diagram, or it is called as Moliere diagram also. Okay, so HS diagram is specific enthalpy versus specific entropy diagram. Okay, and in this case here, point number 1 to 2, if the dry and saturated steam is supplied to the turbine, one point will be there again on curve. Okay, 1 to 2, as it is isentropic expansion, and on x-axis entropy is there. Then 1 to 2 will be entropy, that isentropic vertical line, 1 to 2. But nature of constant pressure line on HS diagram will be inclined like this. So this is nature. So I am here. This is the nature of water inclined 4 to 1. This is the nature of constant pressure line. Okay, so this is related to boiler pressure. This is related to condenser pressure. So 1 to 2 is isentropic expansion from boiler pressure to condenser pressure. Then afterwards, at same pressure, heat rejection is there at constant pressure. So 2 to, it will follow the constant pressure line. 2 to 3, okay, a complete condensation. Therefore, it will give us, yield us complete liquid at point number 3. And 3 to 4, here it will be isentropic compression from condenser pressure to boiler pressure. Okay, and afterwards this is going to be at constant pressure, heating constant pressure here, heat addition or heating of that water, and it is converting into what, dry and saturated steam. If it is converting into superheated steam, as nature is like this, and this is a constant pressure line, we can go on the same line in the superheated zone, 1 dash to 2 double dash. This is a superheated condition. And if it is a wet region, it is going to be 1 dash 2 dash, and 1 to 2 will represent the dry and saturated steam. Now I will ask anybody having problem to understand these diagrams, please ask, because this is the base for our solving the numericals. Anybody, or otherwise if no problem is there, still right, no problem. Have you drawn two answers I want? Whether it is the first answer is whether you are having any problem, and afterwards have you drawn HS diagram of Rankine cycle first. Otherwise, you can you answer fastly in message box. Have you any problem regarding understanding of these diagrams? And second is, have you drawn HS diagram of Rankine cycle? If it is there, I
Sir,
can explain. No problem. Huh?
not drawn, not drawn.
Not drawn, but no problem, na? Understood?
Sir,
हा. प्रथमेश हा. काय असेल ते शंका किंवा काय विदाउट खिचकिच काय बोलायचं काय डायग्राम इज रिमेंट ओके कुणाल एनी ऑर्डर प्रॉब्लेम आहे का अंडरस्टँड का अजून समजावून सांगावं लागतं एकदा
येस सर अजून एकदा
sir,
एक्सप्लेन करा.
explain, sir.
अजून एकदा एक्सप्लेन करू गुड मग ह्याच्यावर एक्सप्लेन करू का पॉवर पॉईंटवर करू एक्सप्लेन मी तुम्हाला समजेल सांगा एक बिंदा
PowerPoint वर, sir.
पॉवर पॉईंटवर करू ओके
पॉवर पॉईंट.
ठीक ओके ठीक आहे देन आय विल एक्सप्लेन विथ द हेल्प ऑफ पॉवर पॉईंट ओके नाउ टीएस डायग्राम एव्हरीबडी अंडरस्टूड टीएस डायग्रामला काय प्रॉब्लेम आहे का एनीबडी टीएस डायग्रामला काय प्रॉब्लेम ती पण एक्सप्लेन करू ठीक आहे 1-2 मिनिटात आपण नो ओके तरी पण 1-2 मिनिटात आपण तर आपण फर्स्ट आपण विल गो फॉर द टीएस डायग्राम 3 केसेस this is going to be TS diagram. So TS diagram nature of constant pressure line is like this. So I will this is related to boiler pressure. If it is condenser pressure. This is nature of here constant pressure line. Okay. So during all this, whatever boiler, all this line, along this line, the boiler pressure is remaining constant. Okay. Along this line, the condenser pressure is remaining constant. Okay. First of all, we will go for the condition that is wet steam. So this construction, when you are drawing in your notebook, you have to draw with very faint line. Okay, very faint line. Okay, then point number 1 is in the wet region because we are supplying wet steam is supplied. Wet steam is supplied to the turbine. Okay, so point number 1 is lies always in the wet region in that case. So point 1 is there. Okay, or afterwards we can give when we are drawing the diagram in common, we are giving the name it as a 1 dash. Okay, so 1 dash to this here we call isentropic expansion. steam turbine. Okay. Then afterwards 2 to 3 as condensation is complete and at constant pressure condensation means heat rejection. Condensation means what? We have to reject heat. 2 to 3 is going to be the heat rejection in condenser. Okay, so that we are going in the condenser. Okay, and 3 to 4, what is 3 to 4 is there? Isentropic compression in pump, because expansion is condensation is get completed, therefore pure liquid is there, and here from this we are going for this here expand compression in pump. Okay, so it is isentropic compression pump. As it is x-axis entropy is there, again it will follow the vertical line, but up to what? This vertical line. Okay, isentropic compression line, it should cut up to boiler, because now we reached from condenser pressure to boiler pressure. So this will ends our point 4. This expansion compression process ends here, and here the process is called as in pump. Okay, and 4 to 1, in this case it will be sensible heating up to this, I can say A. Okay, entire 4A1 4 to 1 is sensible heat, and this is a latent heat. But as steam is, all steam has, all water particles are not converted into steam, some are remained, therefore the steam will be called as a wet steam. Now this everybody understood, I think, no problem for this. So this happens in, I will boiler, B for boiler you can consider. B means boiler, here it is pump, and it will be boiler, turbine, condenser and pump. So this is, I think, diagram everybody got TS diagram. When steam supplied is wet. Fast reply fast so that we can cover more. No, if you are in doubt, I am ready to tell many times, don't worry, but reply so that I will get some. Okay, Gaurav Prathamesh, good. So this is again same diagram, I have to repeat, only the steam is entering to turbine is now not wet. Okay, so it will be, okay, so this dark polygon 1 2 3 4 1, that polygon you have to make dark always in your notebook. Now other construction you have to make with the faint line. Okay, then again same diagram is there, PA diagram only. Okay, but steam entering to turbine is not now here wet, it will be dry and saturated. Okay, now again critical point. So again two lines, same construction, only change with there. This is faint line we make, this is boiler pressure line, this is nature on TH diagram. Constant pressure line is like this, inclined horizontal line, then inclined, like this condenser pressure here, phase change, temperature remaining constant, and afterwards inclined nature. Okay, and this will be condenser pressure. So this again boiler pressure, we can write PB, this is condenser pressure PC, depending on the diagram. Then here 1 to 2, if dry and saturated steam means point number 1 should be always in the on the vapor line, dry and saturated line. Well, every complete conversion is there. Therefore 1 to 2 will be there. I will now draw some fast. 1 to 2 happens in steam turbine. Remaining diagram is same as that of the one, this diagram. 2 to 3 happens in condenser. Okay, and 3 to 4 it will be vertical isentropic. Okay, pump, this will be pump, P for pump and B for boiler, you can consider. Understood, I think, diagram. This also no problem, because only point number wet stream supplied, point number 1 is in the wet region, this is a here in the dry and saturated. The next is TS diagram for steam supplied is superheated. Okay, again nature, boiler pressure, This is nature. Okay, PB. This is nature condenser pressure line also. Same parallel to boiler pressure line. Now steam supplied is not dry or wet. It is not how much superheated. The nature of point or one point number one, where it will be, this is a boiler line, okay, and this is a condenser C, okay. You write condenser, you write boiler, because I am having some problem with this particular mouse as a or my pen, okay, therefore I am getting some problem. So point number one, this is a horizontal line, just refer. Okay, so point number one, inclined line, it will be super. Let's consider this as superheated steam. One point, this happens in now steam turbine. The point number two will be here. 2 to 3, complete condensation in condenser. There is no change. 2 to 3. And 3 to 4, it will be, here it will be no change. Same, 4 in pump. And 4 to this boiler process. Maybe here it will be a sensible heat. Then this will be latent heat. And this will be superheat. So this entire is a 4 to 1 process. It is sensible, latent, and superheat. And this everybody understood. I think this you have drawn, na? Last lecture. We will go for next. This drawn, no problem. Drawn, na? All these diagrams again. Yes, okay. Then next is diagram. We are interested in which diagram? Here, HS diagram. So this is our HS, means y-axis H and x-axis here specific entropy. H, yes, diagram. Specific enthalpy versus entropy. Okay, nature is same. Curve nature is like this only. Okay, that is now it is for our understanding. It will be now like this. Okay, but nature on this HS line, nature of curve is also little bit different. But now for simplicity, we'll consider nature is same. But nature of constant pressure line on this Mollier diagram is not like this. आता तिकडे कसं होतं, असं होता, असा होता, असा होता HTA diagram ला. पण HTA diagram ला nature of constant pressure line is like this inclined line. Okay, this is nature is available of constant pressure line in here TA diagram. Okay, but this is nature is what of constant pressure line in which here HA diagram, because we have changed the coordinates. So here as nature is like this, so it is a boiler pressure line. Okay, another pressure line is there. This is also we have to draw in the faint. Okay, so this is going to be condenser pressure line. Up till this no problem, because this is the nature of constant pressure line on HS diagram, and previously nature was on TS diagram, constant pressure line. Let us consider that point number one is a dry saturated steam. We are supplying dry and saturated steam to the turbine. Again, point number one will be here. So from this here, expansion will start. Vertical line. To make pencil in the card, you have to use scale for drawing these vertical lines, horizontal lines. And point number one is expansion happens in turbine. Okay, but now at constant pressure, this is the constant pressure nature, and constant pressure heat rejection. As heat is rejecting, enthalpy is going to be decreasing, because this is H on y-axis, enthalpy is there. It is decreasing. but at the same time entropy also goes on decreasing. Okay, and 2 to 3 complete condensation will achieve. Okay, at point number 3. Okay, this happens in condenser. Okay, and then afterward 3 to 4 isentropic compression, but from again as y x-axis entropy is there, again vertical line up to what, up to boiler pressure. This will be our 3 to 4, and this happens in pump. Okay, and 4 to 1. Now here there is only pressure line, so this is nature of constant pressure line. Constant pressure heating, heat addition. Therefore enthalpy goes on increasing. As enthalpy goes on increasing, heating, entropy also goes on increasing, and this is a boiler. So this is one diagram when steam supplied is dry and saturated. Okay, if steam supplied is wet, what will be the nature? Where will the point number 1 will tell? Where will the point number 1? Where is the point number 1? कोणी तर सांगा एका ना, लक्ष ज्यांचं आहे त्यांचं.
Towards left side.
Towards left side, because it is a wet region. So shall I draw here only or separate? You can go for point number 1. We can consider it as a 1 dash. Here we can dotted line. If 1 change झाला मग दुसरा 2 पण काय होणार ऑटोमॅटिकली चेंज होणार. त्याला आपण 2 ला आपण काय म्हणू, 2 to 1 to 2 चा चेंज झाला 2 डॅश पर्यंत. ओके, सो 1 डॅश 2 डॅश. ओके, जर सुपरहिटेड असेल तर फक्त ह्या बॉयलर काय फरक होईल, इथं पॉईंट जाईल 1 डबल डॅश आणि कुठला 2 डबल डॅश. हे खाली तुमची 1 डॅश 2 डॅश म्हणजे still again I have lost my basic connection. Understood? आता अंडरस्टूड झालं का? येस. ओके, सगळ्यांनी लिहा. So I will check my connection. Net problem today. Okay, understood. Now this diagram you can draw. Diagram drawn. visible now in all respect, because that my diagram is little, because vertical line etc. are not drawn properly. Kunal, drawn?
Yes, sir.
Okay. Everybody, others, please write yes or not so that I have to move further. बेसिक असल्यामुळे आपण वी आर गेटिंग स्लो. गुड गुड सुहास, गुड शुभम, गुड कुणाल, व्हेरी गुड. Others, please reply. So that 8 to 9 reply I will get, then we will proceed to further. Okay, Rishi Vishnu drawn, Akshay also drawn, Gaurav drawn. Good. Either good. Okay, now shall I go to next point? In efficiency of Carnot cycle. Okay. Write down efficiency of Carnot cycle. Now in this Carnot cycle, as heat addition and heat rejection are not happens at constant temperature, they happens at constant pressure. Therefore, we have to use, when constant pressure heating is there, there we have to use the for calculation of any heat supplied or heat rejection, we have to use the enthalpy as a word, because enthalpy is H is equal to enter energy plus U plus here anybody PV, pressure volume. So at constant pressure, we have to use the term enthalpy. And when the temperature is constant, then we have to use that only temperatures we have to use. Okay. Now here efficiency of Rankine cycle. Write down. Efficiency of Rankine cycle. Efficiency of Rankine cycle is defined as ratio of net work obtained to the heat supplied to the cycle. Shall I repeat? Rankine cycle efficiency can be defined as ratio of net work obtained from cycle to the heat supplied. Okay. Then eta Rankine is equal to W net divided by QS. But we know that everybody is writing, mention or tell. Somebody, shall I ask somebody to write, repeat? Akshay Hetia.
Yes, sir.
Repeat. Efficiency of Rankine cycle.
It can be obtained by efficiency of Rankine cycle is equal to Qs minus Qr divided by Qs.
But before that, I have told definition. Ratio of work obtained from cycle to the heat
supplied.
Okay. And therefore, net work obtained is equal to what? Qs minus Qr divided by Qs. Okay. But Qs is nothing but, what is Qs here? Here, let us consider this as the entropy diagram, HH diagram. So HS, so this enthalpy at point number 1 will consider as the H1. This enthalpy at point number 2 will consider as the H2. Okay. And this point number 3, it will be H3, and point number 4 enthalpy will be H4. You would understand? H1, H2, H3, H4. Okay. And then heat supplied आता हीट सप्लायड कुठं कुठं होते 4 to 1. ज्यावेळेस पॉइंट हा फक्त पंपाकडून आपल्याला वॉटर मिळतं त्याला त्यावेळेस एन्थाल्पी किती असेल त्याची H4. बॉयलरमध्ये ते हीट घेईल त्याची सेन्सिबल हीट, लॅटेंट हीट किंवा सुपर हीट काय असेल ते, आणि तो कन्वर्ट होईल स्टीमशी. तर किती त्यावेळेस एन्थाल्पी किती असेल H1. बॉयलरमध्ये किती हीट घेतली त्यानं, हाऊ मच हीट इज ॲडेड इन बॉयलर, एनीबडी? हीट सप्लायड किंवा हीट ॲडेड किती होईल? अनम्यूट करा आणि सांगा कोणी. बॉयलरमध्ये येताना त्याची एन्थाल्पी आहे H4, जाताना आहे त्याची म्हणजे तयार झाला स्टीम तयार झाल्यानंतर त्याची एन्थाल्पी आहे H1. म्हणजे काय स्टीम असेल
H1
वेट
minus
असेल
H4.
H1 मायनस H4. तसंच ज्यावेळेस तो कंडेन्सर मध्ये येते ती आपल्याला स्टीम, त्यावेळेस त्याची एन्थाल्पी किती असते H2, जाताना
H2 minus
H2
H3.
मायनस H3. म्हणजे हीट सप्लायड किती येणार H1 मायनस H4 आणि हीट रिजेक्टेड किती येणार H2 मायनस H3. ओके. तसंच आता ज्यावेळेस आपण टर्बाईनला आपण सप्लाय करतो हीट दॅट आपण स्टीम, त्यावेळेस त्याची एन्थाल्पी किती असते H1. ज्यावेळेस टर्बाईन मधून जाते एक्झिट होते त्यावेळेस त्याची एन्थाल्पी किती असते H2. वाय ऍक्सिसला H आहे, ड्रॉस्टिकली एन्थाल्पी डिक्रीज होते म्हणजे ती कशामध्ये कन्वर्ट होते, कशामध्ये कन्वर्ट होते वर्कमध्ये. म्हणजे H1 मायनस H2 म्हणजे काय, W स्टीम काय होईल तो W स्टीम. ओके. आणि H3 कॉम्प्रेसरवर किती असणार आहे H4 मायनस H3. तर तसंच म्हणजे आपण आता इटा रँकिन इज इक्वल टू QS मायनस QR डिवाइडेड बाय QS. QS किती आहे आपला हीट सप्लायड H1 मायनस H4. QR किती आहे आपला हीट रिजेक्टेड किती आहे H2 मायनस H3. H2 मायनस H3 आणि हीट सप्लायड H1 मायनस H4. ह्याचा जी रेशो आहे H1 मायनस H4 मायनस H2 मायनस H3 divided by H1 minus H4. With the help of this formula, one can calculate efficiency of Rankine cycle. पण लिहिले तुम्ही बाकी एव्हरीबडी अंडरस्टूड, एनीबडी हॅव्हिंग प्रॉब्लेम? हीट सप्लायड H1 minus H4, H2 minus H3 आणि रँकिन सायकलची इफिशियन्सी देअरफॉर H1 minus H4 मायनस इन ब्रॅकेट H2 minus H3 डिवाइड बाय H1 minus H4. काय प्रॉब्लेम असेल तर पटकन विचारा, डोंट हेजिटेट. समजलं असेल तर येस लिहा प्लीज, नसेल समजलं तर विचारा. व्हेरी सिम्पल. येस, गुड. ओके, सो फॉर्म्युला ऑफ रँकिन सायकल इफिशियन्सी, मेक स्क्वेअर ब्रॅकेट फॉर दिस. मेक स्क्वेअर ब्रॅकेट लिहून घेताय, 1 मिनिट देतो मी तुम्हाला. रिटर्न. ओके. दुसरा एक फॉर्म्युला, हाच फॉर्म्युला आपण मॅथमॅटिकली रिअरेंज करू शकतो. काय H1 मायनस H2 आणि मायनस H4 मायनस H3. आज फक्त कशाबद्दल लिहितोय आपण लक्षात ठेवा. तर इफिशियन्सी ऑफ रँकिंग सायकल लिहा, हे सगळं लिहून काढा. इफिशियन्सी ऑफ रँकिंग सायकल also can be defined as ratio of net work obtained from cycle to the heat supplied. नेटवर्क म्हणजे काय, जे टर्बाईन डेव्हलप केलेलं वर्क आहे ते पॉझिटिव्ह असतं. पंपला जे वर्क आपण देतो त्याला निगेटिव्ह असतं. म्हणजे पॉझिटिव्ह आणि निगेटिव्ह म्हणजे नेट किती असणार, पंपानं तयार केलेलं टर्बाईननं तयार केलेलं मायनस पंपाला दिलेलं, व्हॉट एव्हर गिव्हन फॉर पंप. दॅट डब्ल्यू स्टीम आणि डब्ल्यू पंप विल रिप्रेझेंट नेटवर्क. सो अनादर फॉर्म्युला काय लिहा, इफिशियन्सी ऑफ रँकिंग सायकल can also be defined as ratio of net work obtained from cycle to the heat supplied. Heat ranking is equal to W net divided by heat supplied, WST minus W pump. इथपर्यंत झाल्यावर मग सांगा, आपण विल गो टू दॅट डायग्राम. डब्ल्यू स्टीम टर्बाईन काय आपला, तर H1 एन्थाल्पी किती येते त्या टर्बाईनला, H1 बॉयलर स्टीमची. जेव्हा जो स्टीम जाते टर्बाईन मधून तेव्हा एन्थाल्पी किती असते, H2. जास्त कुठल्या H1, कमी कुठल्या H2, दोघांतला फरक म्हणजे काय, वर्क ऑप्टेंड H1 मायनस H2. म्हणजे इथं वर्क H1 मायनस H2 इज नेट स्टीम टर्बाईन वर्क मायनस H4 मायनस H3 म्हणजे कॉम्प्रेसरला सप्लाय केलेलं वर्क. ओके, किंवा हाच फॉर्म्युला आपण काय करतोय, पहिला H1 मायनस H4 H2 हा रिअरेंज केला की हाच फॉर्म्युला येतो, H1 मायनस H2 मायनस H4 मायनस H3 डिवाइड बाय हीट सप्लायड H1 मायनस H4. हाच फॉर्म्युला मॅथमॅटिकली जरी आपण रिअरेंज केला तर वी आर गेटिंग दिस फॉर्म्युला. ह्यापैकी हा तर रिमेंबर करा किंवा हा रिमेंबर करा, इफिशियन्सी विल कम सेम. याच्यामध्ये काय अडचण, कोणाला अडचण नसेल तर नो म्हणा, वी विल गो टू फर्दर. लिहिलंय का सगळ्यांनी बघा. रिप्लाय पुढे जायचं. येस कुणाल, अदर्स रिप्लाय प्लीज फास्ट, रिप्लाय फास्ट. सगळं लिहिलं का इथपर्यंत मी, सुहास अँड कुणाल नो प्रॉब्लेम, सचिन सुतार नो प्रॉब्लेम. ओके, केदार कुणाल अक्षय नो प्रॉब्लेम. शुभम नो प्रॉब्लेम. Okay, then write down, this is next actual ranking cycle. This student has written RANKIN E, you write always E, actual ranking cycle. Actual ranking cycle, and write down this 4 to 5 lines. Actual Rankine cycle. Made heading. Have you made heading actual Rankine cycle? Yes. Okay. Written over. Okay. Like this, Kunal, you reply over. Write up over. Okay. Shubham, Kunal. Okay. Okay. Over. Okay. Now what happens in our Carnot cycle? We have considered one of the limitation of Carnot cycle that due to friction present in turbine and compressor, their compressor, the expansion and compression are not isentropic. But here also, Rankine cycle also considered this expansion and compression are isentropic. But due to friction present in the turbine and pump, expansion and compression processes are not isentropic in actual case. Very important. This is actually theoretically we can consider turbine and compression both are isentropic. Theoretically, we can consider, but actually, they are not. Okay. Therefore, okay. Before that, you draw the diagram. So let I mean some work. Okay. 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 Let us. Okay. So what happens here? So 3 to 4 that here actually this 1 to 2 process is not remaining isentropic. This will remain a little bit anisentropic. Means there is always entropy is increases during this process. So 1 to 2 will be like this, okay, inclined. It will not going for vertical, and 3 to 4 also not going for same vertical. It is also going for some inclination, change. Okay, so that girl has made mistake here. Student here made mistake. So therefore, I will show you through our PPT diagram. Oh, what happens? Let us consider this as a board diagram. We will draw here only TS diagram. Okay, this is one of the example. Therefore, let us consider that steam is dry and saturated supplied to the turbine. Let us consider. So this we know that this is the nature of constant pressure line. TS diagram. Okay. So this is the nature of constant pressure line. Okay. This is boiler pressure P boiler. Condenser pressure P condenser. Okay. Let us let us consider steam entering to the turbine is dry and saturated. So this is 1 to 2. Point number one. This is point number two. Okay. Then 2 to 3 condensation in condenser. complete condensation. Then 3 to 4. Okay, 3 to 4. You will redraw with the scale. This is happens in boiler. I'll write, you write, I am writing short B means boiler, you write turbine ST, no problem. You write condenser as C means condenser completely, and here you write pump. Okay, boiler, condenser, pump, and turbine. You write the whole letter. Now, actual case, this is theoretical cycle. This is theoretical Rankine cycle. Actual Rankine cycle, what will happen? The process 1 to 2, due to friction in turbine, will not remain isentropic. So there will be little bit change. So I am dotted line. So this will be point number 2. Will shift from 2 to 2 dash, right hand side. 2 to 2 dash. So 1 2 dash 3, and after again 3 to again here this also process. The point number 4 will shift to 4 dash because there is a friction in between pump. Therefore this 1 dash 2 dash 3 4 dash 1. So this represent 1 2 dash 3 4 dash 1. So this represent actual Rankine cycle. What happens? 1 to 2 will not remain isentropic, will be inclined. 1 dash 2 dash. 3 to 4 will be also not inclined. 3 to 4 dash. Okay, if we draw this cycle on HS diagram, okay, then in that case HS diagram is like this nature. This is थोडं वेगळं असतं. Okay, this is our boiler pressure PB. This is our condenser pressure PC. Okay, then here 1 to 2 will be, it happens in turbine. हा सर लेक्चर चालू आहे माझा, बोला की. हा हा हा
डिपार्टमेंट तर्फे म्हणजे मी स्वतःच शाल आणि हार आणला होता, तुम्हाला न्यावं म्हटलं.
नाही तुम्ही जाऊ नये लेक्चर.
सर सोनवणे सर पारखे सर चौघ
नाही जाऊ नये.
मी घेतली नाही मोठा.
हां चालतं, जाऊन जाऊन.
हो.
Okay, so 3 to 4, 2 to 3 is our heat rejection in condenser. I am writing C. Okay, and sorry, here it will be 3 to 4 is in pump. I am writing C means condenser. You write down C means condenser, pump means P means pump. This is boiler. This is our HS diagram of theoretical Rankine cycle. 1, 2, 3, 4. Because these two processes we have considered theoretically as isentropic, but in actual case these are not isentropic. What happens now? This will also not remain isentropic. So you see inclined. This will be 2 dash. This will be again 4 to 4 dash. So this will also not remain isentropic. This will be inclined. So 1 2 1 2 dash 3 4 dash. This will be changed. Others will remain same. So here also 1 2 dash 3 4 dash 1 represent what? Actual ranking cycle. Okay. Now, due to friction present, turbine will develop less work or more work. कोण सांगते? फ्रिक्शन असल्यामुळे टर्बाइन आपल्याला कमी वर्क तयार करेल का जास्त वर्क तयार करेल?
लेस वर्क.
लेस वर्क म्हणजे ऍक्च्युअल वर्क डेव्हलप्ड बाय टर्बाइन विल बी और एच ओके टर्बाइन एच ऍक्च्युअल स्टीम टर्बाइन ह्याचं काय फॉर्म्युला लिहिलं आपल्या इथं या डायग्राम मध्ये H1 मायनस H2 हा थिरॉटिकल झाला आणि ह्याच्यामध्ये काय येईल H1 मायनस काय येईल
H2 डॅश.
H2 डॅश करेक्ट H1 मायनस H2 डॅश आणि ऍक्च्युअली थिरॉटिकली किती येईल तो H थिरॉटिकल स्टीम टर्बाइन आपला किती असतो नेहमीचा H1 मायनस H2 आता हा काय आहे दिस इज ग्रेटर दिस इज स्मॉलर आय विल राईट दिस स्मॉलर ओके म्हणजे H1 मायनस H2 डॅश इज लेसर दॅन H1 मायनस H2 सो वी कॅन राईट हिअर H1 minus H2 dash is greater is smaller than म्हणजे actual work developed by turbine will be less than the theoretical work. Okay. Similarly, पंप आता पंपला वर्क लागतंय म्हणजे फ्रिक्शन मुळे पंपला ज्यादा वर्क लागेल का कमी लागेल
जास्त.
जास्त म्हणजे एच ऍक्च्युअल पंप P means pump you consider it is equal to what H4 dash minus H3 okay and H theoretical pump is equal to Kyle H4 minus काय असतो H3 आता H4 dash minus H3 this will be always जास्त लागतो ऍक्च्युअल वर्क आणि थिरॉटिकल वर्क काय नेहमी कमी लागतो म्हणजेच काय कुठला कमी जास्त आहे तर H4 my theoretical work is always lesser than जास्त कुठल्या ऍक्च्युअल केसला जास्त लागतो you understand this म्हणजे ड्यू टू फ्रिक्शन प्रेझेंट टर्बाइन विल डेव्हलप लेस वर्क दॅन द थिरॉटिकल आणि पंप नीड मोर वर्क दॅन द थिरॉटिकल म्हणजे ऍक्च्युअली पंप नीड मोर वर्क अँड टर्बाइन विल डेव्हलप लेस वर्क बिकॉज ऑफ द फ्रिक्शन आणि हे दोन दोन रेशो जे आहेत कुठले सॉरी these ratios are called as now here I have written HW actual work done by actual turbine okay WST actual is less than WST theoretical okay means H1 minus H2 dash is lesser than H1 minus H2 पंपाचा वेगळा आहे W pump actual is greater than W pump theoretical H4 dash because पंप ला वर्क द्यावं लागतं टर्बाइन वर्क तयार करतो H4 dash minus H3 is greater than H4 minus H3 आता मिनिमम टू मॅक्झिमम याच्यानुसार आपण काय करतो याला डिफाइन वी आर डिफाइनिंग isentropic efficiency of turbine. आता इफिशियन्सी म्हणजे रेशो काय असतो, लहान क्वांटिटी टू मॅक्झिमम क्वांटिटी. म्हणजे इट शुड कम लेस दॅन 1 येण्यासाठी काय लागतं, न्यूमरेटरला नेहमी काय लागते, लहान क्वांटिटी, आणि डिनॉमिनेटरला मोठी क्वांटिटी. तर आता टर्बाईन इफिशियन्सी डिफाईन करायची आपल्याला, तर कशी करतोय आपण बघा. आयसेंट्रॉपिक इफिशियन्सी ऑफ टर्बाईन, ठीक आहे, इफिशियन्सी रेशियो ऑफ मिनिमम क्वांटिटी टू मॅक्झिमम. आयसेंट्रॉपिक इफिशियन्सी ऑफ टर्बाईन इज डिफाइंड ॲज रेशियो ऑफ, कुठलं वर्क जास्त त्यामध्ये कमी आहे, ऍक्च्युअल वर्क डेव्हलप्ड बाय टर्बाईन टू द थिरॉटिकल. म्हणजे डब्ल्यू आयसेंट्रॉपिक इफिशियन्सी ऑफ टर्बाईन इज इक्वल टू WST ऍक्च्युअल डिवाइड बाय WST थिरॉटिकल. म्हणजे therefore isentropic efficiency of turbine is equal to H1 minus H2 dash divided by H1 minus H2. आता पंपच्या बाबतीत कसं होईल, कमी काय आहे, थिरॉटिकल वर्क. इट इज डिफाइंड ॲज रेशियो ऑफ थिरॉटिकल वर्क रिक्वायर्ड टू रन द पंप टू ऍक्च्युअल वर्क रिक्वायर्ड फॉर पंप. आणि मॅथमॅटिकली मग काय येणार, पंप थिरॉटिकल याच्या उलट, कारण हे तयार करतो याच्या उलट, W थिरॉटिकल पंप आणि इकडं W ऍक्च्युअल पंप. याच्यानुसार H4 मायनस H3 डिवाइड बाय H4 डॅश मायनस H3. आणि ऍक्च्युअल इफिशियन्सी अशीच काढायची, QS मायनस QR, फक्त H4 मायनस H4 डॅश मायनस H2 मायनस ब्रॅकेट टाका, H2 डॅश H2 मायनस H3 डॅश डिवाइड बाय H4 मायनस H4 डॅश. Everybody understood this? Any hearing problem? Okay, first I will draw a TS diagram. Understood? Yes. Kunal is understanding. Others please reply. And draw this diagram first. एवढीच पण डायग्राम काढा, बाकीचं वहीमधलं आपण लिहूया याचं, कारण ती डायग्राम त्या मुलींनी चुकली. इथं पॉईंट नंबरवर किंवा 3 to 4 सुहास आणि कोणाला दोघाला समजले, बाकीच्यांना 3 to 4 डायग्राम काढा आधी TS. बाकीचे याचे डायग्राम तिकडे काढूया. बम ऋषिकेश गुड. TS डायग्राम ड्रॉ, आणि TS डायग्राम ड्रॉ केल्यानंतर मला येसचा रिप्लाय द्या. HA diagram will draw that HA diagram that student has written drawn correctly. TS मध्ये फक्त त्यांना चूक केलेली आहे, 3 पॉईंट चुकीचं केलं, त्यामुळे 3 पॉईंट पासून तो इमर्जिंग लाईन दाखवते. Drawn. Then we'll go to okay. Shubham Singh had drawn. Yes, okay. Then okay, we'll shift to our notebook. Okay. So this diagram everybody drawn. Then write down HS diagram of Rankine cycle, actual Rankine cycle. HS diagram, or give heading only HS diagram. ड्रॉ दिस ऑल्सो. हे पण ड्रॉ केले. Diagram drawn. It's a diagram. Diagram drawn. This diagram also drawn. It's a diagram. Yes. Others, please write reply. Okay, then write down. From HS diagram, right, W steam turbine, ST means steam turbine actual, WST actual वर्क काय असतं नेहमी कमी करणार वर्क डेव्हलप टर्बाइन फ्रिक्शनमुळे ड्यू टू एच फ्रॉम एच डायग्राम इन ब्रॅकेट राईट डाऊन ड्यू टू फ्रिक्शन फ्रॉम एच डायग्राम ड्यू टू फ्रिक्शन WST actual is less than WST theoretical. टर्बाइन ST म्हणजे स्टीम टर्बाइन वर्क ऍक्च्युअल आणि थिओरिटिकल. दॅट इज WST ऍक्च्युअल काय आहे H1 मायनस H2 डॅश. Therefore H1 minus H2 dash is less than theoretical काय H1 minus H2. theoretical म्हणजे our cycle ideal cycle आपण फ्रिक्शन केलं नाही एज्युम केलं नाही. H1 minus H2 dash less than H1 minus H2. पंपच्या बाबतीत काय होईल W pump actual is greater than जास्त लागेल आपल्या पंपवर ऍक्च्युअल पेक्षा. W pump actual is greater than W pump theoretical. W pump actual is greater than W pump theoretical. That is H4 dash minus H3 is greater than H4 minus H3. Understood? Then write down now. Isentropic efficiency of turbine. Isentropic efficiency of turbine. Isentropic efficiency of turbine. In bracket eta isentropic. Eta st or eta isen st. In top margin कुठेतरी लिहा वर समासात इथे लिहून आलं लगेच. Efficiency is always ratio of minimum to maximum, minimum quantity to maximum quantity. ती लेस देन 1 असल्यामुळे आपण जनरली वर टेक रेशो ऑफ मिनिमम क्वांटिटी टू मॅक्झिमम क्वांटिटी. Therefore, isentropic efficiency of turbine is defined as ratio of actual work developed by turbine to the theoretical work developed by turbine. Actual कमी आहे theoretical जास्त आहे म्हणून ratio of actual to theoretical. Isentropic efficiency of turbine is defined as ratio of actual work developed by turbine to the theoretical work developed by turbine. Okay. Therefore, eta isen st is equal to Kyle WST actual divided by WST theoretical. पण WST actual काय आपला H1 minus H2 dash आणि theoretical काय H1 minus H2. Understood? डेफिनेशन सगळ्याला अंडरस्टूड केली मिळाली झाली का फॉर्म्युला सहित. Because when sometimes they are going to ask the numerical on actual ranking cycle. Understood? Reply. Okay, Kunal, no problem. Others सगळं लिहून घेतले आणि अंडरस्टँड केले. अंडरस्टँड झालंय. Others please reply. सुहास, कुणाल, नो प्रॉब्लेम. लिहून पण घेतले आणि अंडरस्टूड झाले. दोघांना झाले, बाकीच्यांना others शुभम. ओके, केदार यादव, नो प्रॉब्लेम. लिहून घेतले आणि केले. टुडे आय थिंक नो गर्ल स्टुडंट्स आर प्रेझेंट. आय थिंक निकिता पवार एटसेट्रा. Shubham Singh, yes. Okay, then we'll go to the next definition. Okay, then add on isentropic efficiency of pump. Isentropic efficiency of pump. Hold on. It is defined as ratio of ratio of theoretical work. Isentropic efficiency of pump, we are writing eta isen pump in bracket. It is defined as ratio of theoretical work required to run the pump. Ratio of theoretical work required to run the pump to the actual work required for the pump. Theoretical लहान आहे आणि actual काय आहे जास्त आहे. It is defined as ratio of theoretical work required to run the pump to the actual work required to run the pump for pump. Mathematically, eta isentropic pump is equal to W pump theoretical divided by W pump actual. It is defined the ratio of theoretical work required to run the pump to the actual work required for pump. Mathematically, eta Sn pump is equal to W pump theoretical divided by W pump actual. Theoretical pump चं काय आपलं फॉर्म्युला H4 minus H3 and pump actual pumpचा H4 dash minus H3. So the point number 2 is replaced by 2 dash and 4 will be replaced by 4 dash. Everyone understood? Again I'll repeat. Isentropic efficiency of pump, it is defined as ratio of theoretical work required to run the pump to the actual work required for pump. Sorry, to run the pump. Actual work required to run the pump. Mathematically, eta Sn pump is equal to W pump theoretical divided by W pump actual. And therefore is equal to H4 minus H3 theoretical work and actual काय H4 dash minus H3. Understood? Any return reply? Good, Gaurav, good. Now Gaurav comes. Okay, good. Okay. Now, actual Rankine cycle efficiency can be calculated as actual Rankine cycle efficiency can be calculated as actual Rankine cycle efficiency can be calculated as write down actual Rankine cycle efficiency. Write with me. Eta actual Rankine is equal to again formula heat supplied QS, actual heat supplied QS minus actual heat rejected QR divided by QS. Let us consider this formula. Eta actual Rankine is equal to QS minus QR divided by QS. Now, in actual Rankine, so eta was here. Okay, is equal to actually how much heat is supplied? कोण सांगते? Actually heat supplied किती येता इथं? Point number 4 will be replaced by कोण सांगते? H1 किती आहे? H1 minus H4 dash. H4 H1 minus H4 dash. H1 minus
H1 minus H2 dash.
H4 minus H4 dash बरोबर आहे ना? Actual heat supplied आहे. ओके मायनस heat rejected किती येणार? H2 minus H3. पण पॉईंट नंबर 2 इज रिप्लेस्ड बाय काय असेल? काय असेल? H2 dash minus H3 and divided by H1 minus H4 dash. With the help of this formula, one can calculate the actual efficiency of Rankine cycle. फक्त आपल्याला पॉईंट नंबर 2 H2 dash आणि H4 dash we have to calculate. असे पण काढू शकता तुम्ही. W टर्बाइन मायनस पंप H1 मायनस H2 डॅश मायनस टर्बाइन पंप स्कॅनर H4 डॅश मायनस H3. हे तर फॉर्म्युला आपण रिराईट केला तर असा पण होऊ शकतो. आफ्टर रिरायटिंग किंवा टर्बाइनचा इफिशियन्सी मायनस आहे H1 मायनस H2 डॅश मायनस H4 डॅश मायनस H3. And divided by heat supplied H1 minus H4 dash. हे दोन पद्धतीचे फॉर्म्युले आहेत. W टर्बाइन मायनस पंप डिवाइड बाय हीट सप्लाइड किंवा हीट सप्लाइड मायनस हीट रिजेक्टेड डिवाइड बाय हीट सप्लाइड. एनीबडी एनी प्रॉब्लेम? ओके, अंडरस्टूड. ऍक्च्युअल रँकिंग सायकल इफिशियन्सी नेहमी काय असणार? जास्त असणार, कमी असणार थिओरिटिकल पेक्षा? फ्रिक्शन आहे म्हणल्यावर कोण सांगते?
कमी असणार.
कमी असणार, करेक्ट. कारण फ्रिक्शन असल्यामुळे पंपला जास्त वर्क लागते आणि टर्बाइन कमी वर्क डेव्हलप करतो. ओके, विथ दिस शॅल वी कन्क्लूड टुडेज लेक्चर. अंडरस्टूड झाले का? आधी लक्षात द्या, रिमार्क द्या. ऍक्च्युअल रँकिंग सायकल एव्हरीबडी अंडरस्टूड? लिहिले आणि एक सगळं अंडरस्टूड झालं? येस. ओके, now we'll conclude today's lecture now, but before that I have to take the attendance. Everybody return. Today any program is there? Any type of program? Okay, roll number 1 to 10, unmute. 1. Absent, present, absent. 1 to 2, 1 to 10, unmute. 1 absent. 2. Absent. 3.
Present, sir.
3 is present, Gaurav. Okay. 4. 5. 6.
Yes, sir.
5 present. Okay. 6 absent. Okay. 7. 8. 9. 10. 11 present. Am I right?
Yes, sir.
Okay. 12. 13. 14. 15. 16. 17.
Present.
present. Okay, Rishikesh, good. 18.
Present, sir.
18 also present. Sachin Sadar, good. 19. 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30.
30 present, sir.
Okay, 30 present.
Present,
Okay,
sir.
Shinde, Saurabh, I got 31, 32, 33, 34.
34 present, sir.
Okay, 35,
Yes, sir. 35.
36, 35 present, 36. Shubham, I got. Okay, 36, 37.
Present, sir.
Okay, Soham. Okay, I got it. 37, 38, 39, 40,
Present, sir. 40.
40 present. Okay, 41, 42, 43, 44, 45, 46.
Yes, sir.
Okay, get out here. Present 46, 47.
47. Yes, sir.
Okay,
47.
48. Okay, I got it. Bhupendra. 48, 49, 50.
Present, sir.
Okay, Akshay. Okay, uh,
Yes, sir.
50, 51, 52, 53,
Yes, sir.
54,
53 present.
53. I got it. 54, 55, 56, 57 present, I think. 57, 58,
Yes, sir. 58 present.
58 present. Okay. 59. Okay, 58
59
present.
present, sir.
Okay. 59 present. Balaji present. 60,
Present, sir. 60.
60 present. 61,
Yes,
57
sir, present. Yes, sir, 61.
present. Go. Okay. 57 is present. Okay. 62, 63, 4,
65,
5,
sir.
65. Kunal present. Okay. 66. Okay, Kunal, I got it. 66, 67.
Yes, sir.
Okay, fine.
Yes, sir.
67, 68, 67 present, 68 absent, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78. Okay. So with this, I think, shall we close?
Sir, 34 is taken.
34.
4.
You are present.
Okay, sir.
Okay, then we'll see.